now let us dive a little bit more towards the theory side. So in the rest of the lecture today, what we are going to focus on is how to go from the electronic properties of individual atoms to the electronic properties of van der Waals heterostructures, of a twisted van der Waals heterostructure. So the question is, how do we start with the Schrödinger equation for an individual atom, understand what are the electronic properties of a 2D material, and then afterwards take the electronic structure of a 2D material and understand what is the emergent phenomena that we see in a van der Waals heterostructure. So essentially, we need to make two steps. The first step is something that we are already very much used from solid state physics, of course. And the next step is actually very similar to the first one. But that is, of course, something that we will go in detail during the exercises. All right, good. So let us now go with the theoretical tools. And in the next, let's say, 10-15 minutes, we are essentially going to focus on 3 theoretical tools. And this is a reminder because, of course, you already know about this, but I think that it's good to mention it just so that we are all in the same page. So first one, we will review second quantization, electronic structure theory, and beam field theory.
We should practice raising hands. So how many of people know about second quantization? Raise your hand. Yeah. So not everybody.
Yeah. All right. Good. Yeah. All right. So then it's great to review this now. Yeah. And as I mentioned before, please, if there are any questions, don't hesitate interrupting me and asking, of course. All right, great. So the basic object that we know to describe materials and to describe atoms is, of course, the Schrödinger equation, right? So the typical object that we have in quantum mechanics. So we have our Hamiltonian, a wave function, and essentially the basic idea that we need to compute the eigenenergies of this Hamiltonian. And of course, we usually distinguish between 2 different types of Hamiltonians: Hamiltonians that are effectively single particle and Hamiltonians that are many body. Single particle Hamiltonians are the easiest ones. Many body Hamiltonians are the hardest ones. And typically, if you want to see emergent phenomena or some things like magnetism, superconductivity, or more unconventional correlated states, then many body phenomena is what it's playing a role. So we need to be able to understand both single particle and many body. But let's start with, let's say, the formalism that allows us to understand both at the same time. All right, good. So this is essentially the idea of second quantization. So for single particle phenomena, you're essentially describing all the time wave functions of individual electrons that are completely uncorrelated. So you just need to have mathematical objects that tell you about one single electron at a time. And that is why this is called independent particles or free particles or free theory. And in those cases, we can, of course, use just first quantization, which is the typical formalism that we have in quantum mechanics. But if you now start having interactions, it can be repulsive interactions, it can be attractive interactions, then electrons are no longer independent. Then you cannot consider anymore that one electron has a wave function that is completely uncorrelated with the wave function of another electron, but you need to start writing down wave functions in which the positions of the 2 electrons depend from each other. And let's say a very simple and maybe minimal example is the following. So let's imagine that you have a quantum state that has at the same time no electrons whatsoever and 2 electrons at the same time. So this state that it's clearly correlated, right? Because if you know if you have one of the electrons, then you know if you have the other, and vice versa at the same time. So if you measure the system and you see that you have no electron in the first level, then you automatically know that you have no electron in the second level. But this kind of wave function is something that it's relatively hard to describe using first quantization, using the type of wave function that we are used to in quantum mechanics. And for this type of states is why we use second quantization. So second quantization allows you to simultaneously describe states in which you have one electron in one level and states in which you may have let's say no electrons and several electrons at the same time. So even a fluctuating number of electrons. So it's not only about correlation, but you can also have wave functions with a non-constant number of electrons. That, of course, it will be important for superconductivity. All right, so let's start with the simplest case. So let's consider that we have a particle in a box system, you can think that it's a quantum dot or that it's an atom or any other quantum system. The important thing is that you have ordered levels. So you have E0, E1, and E2, for example. And they are, of course, the eigenstates of a single particle Hamiltonian. So now if you focus just on the first two levels, and you think about the states that have a single electron, you may consider these two states. You can think about the state in which the electron is in the lowest state, so an electron in E0, and then one state in which the electron is E1. And according to first quantization, we just say that the electron in E0 is the wave function 0, the ket 0, and the electron in state 1 is just the ket 1. So now the basic idea is how we are going to write down a formalism that, apart from describing those states, allows us to describe a state in which you have no electrons in the two levels and two electrons in both levels at the same time. And before going to the mathematical formalism, let me emphasize why states like that, states that can have a fluctuating number of electrons are important. So, of course, quite often in physics, we think that charge is conserved, and certainly charge is conserved, right? So we, first of all, shouldn't think that the electrons are fluctuating, right? We have 100 electrons, we don't have 120 and then 80 and then 120 and 80, right? Charge is conserved. But many times when we work with the effective description of materials, and in particular in many body Hamiltonians and of course in superconductors, the effective Hamiltonians that we get do have a fluctuating number of electrons. And maybe two very good examples is in the case of magnetic materials. So when you try to understand the coupling between different magnetic atoms, it is actually very useful to think about a fluctuating number of electrons in each atom, and that gives rise to what is called the Goodenough-Kanamori rules that in particular govern the magnetic order of, let's say, chromium triiodine, chromium tribromide, many other two-dimensional magnetic materials, and so forth. And of course, in the description of superconductivity, we have a Hamiltonian that intrinsically breaks down the electron conservation number. All right, good. So now let's go towards the mathematical formalism. So the idea of second quantization is actually very, very simple. So instead of thinking about wave functions, let's start thinking about objects that create and destroy electrons. And in particular, we essentially define two different objects. One object that is what we call the annihilation operator. That what it does is it annihilates an electron, it destroys an electron, it takes a state that has an electron and turns it into a state that has no electron whatsoever. And then the other operator is the creation operator. And what it does is, of course, to create an electron. It takes a state that has no electron and turns it into a state that has one more electron. And the basic idea that apart from these objects that are the creation and annihilation operators, we also define an object that is the ground state wave function. That it's the wave function of the entire system, of the entire universe, if you want to say, that has no electrons whatsoever. Meaning that when you try to destroy an electron in this state, you just get 0 because the state didn't have any electron. So the basic idea now is that with this creation and annihilation operators, you can essentially write down every Hamiltonian that you need. And for example, if you want to describe an atomic dimer with a single electron, in which an electron is jumping from atom number 0 to atom number 1, you can essentially write down that Hamiltonian just at C dagger 0, C1, namely that an electron gets destroyed inside 1 and it gets created inside 0. And the Hermitian conjugate is that an electron gets destroyed inside 0 and it jumps to site 1. So this Hamiltonian is a Hamiltonian that conserves the number of electrons, but it just describes a single electron that is jumping from one side to the other. So this is the type of Hamiltonian that we usually call a single particle Hamiltonian. All right, so now the basic idea is that every single state that you thought about in first quantization, namely a state with 0 electrons, a state with 1 electron, a state with 2 electrons, and so forth, can be written with this very same creation and annihilation operators. So the vacuum state that we called omega is by definition the state that has no electrons whatsoever, so it gets destroyed every time that we apply an annihilation operator, then if you want to think about a state that has just one electron in the lowest state, you just write C dagger 0, your ground state. If you now want to think about a state that has one electron in the first excited state, you write as C dagger 1, your ground state. And then if you want to write one state that has 2 electrons, you just multiply your 2 creation operators. So now the basic idea is that these operators, you also enforce in them some algebraic constraints. And in particular, the algebraic constraint that you enforce is that C dagger I Cj, its anti-commutator is just the delta function, namely that if they are on the same orbital, on the same site, you get 1. If they are on different, you get 0. And even though this looks like something fairly artificial, let me just mention that this is the way in which you guarantee that you do not violate Pauli statistics. So if you enforce this mathematical property, you automatically get Pauli statistics from this. And of course, this is something that we certainly want in a wave function for electrons. So essentially, this is everything that you need to know for second quantization. We have creation and annihilation operators, and we can write down any Hamiltonian in terms of them. And as always, if we want to solve a Hamiltonian, we just have to diagonalize it. All right, great. So now that we know what are our creation and annihilation operators, we can know what is a single particle and a many-body Hamiltonian. So a single particle Hamiltonian is just a Hamiltonian that is quadratic in creation and annihilation operators, namely that you have one annihilation and one creation, and then you can have, of course, a whole collection of different numbers that multiply the different combinations. So in that Hamiltonian that you see on the top, Tij is just a set of complex numbers. And of course, C dagger and C are the creation and annihilation operators. So those type of Hamiltonians are the easiest ones to solve. And in short, the only thing that we need to do to solve those Hamiltonians is just to diagonalize the matrix Tij. So if you diagonalize that matrix, then you automatically can write the Hamiltonian in the diagonal basis, where the eigenvalues of your Hamiltonian are just the eigenvalues of the matrix Tij. And then, of course, we have also many-body Hamiltonians. So Hamiltonians that are no longer quadratic in the creation and annihilation operators, but they are actually biquadratic. So they have 2 creation operators and 2 annihilation operators. So the typical many-body Hamiltonian that you can think about is, for example, a density-density interaction that comes from Coulomb interaction. So the density operator is C dagger C. If you write density-density, that's C dagger C, C dagger C. So in total, 4 creation and annihilation operators. So that interaction term that you see there is, for example, one of these many-body terms that we can have. And what is important is that once you have a term like that one, solving the Hamiltonian is not so easy anymore. You can still diagonalize that matrix. There's nothing wrong with diagonalizing that matrix. The problem is that writing down the basis in which you need to diagonalize the matrix is much more computationally expensive. And in particular, it grows with exponentially with the number of orbitals that you have. It is still doable, but it's much more challenging. So in the first case, the matrix that you have to diagonalize is just linear on the number of orbitals that you have. So if you have 100 orbitals, you just have to diagonalize a matrix that's 100 times 100, which is very easy. In the second case, if you have 100 orbitals, then you have to diagonalize a matrix that is 2 to the 100, which is not so easy anymore and not doable in most instances in practice. So to deal with this type of Hamiltonians that are biquadratic and that are responsible of most of the phenomena that we will see in two-dimensional materials, we need some approximation. And this approximation is mean field theory. Yeah, that's a very good question. So the basic idea is that the reason why you want to diagonalize a Hamiltonian is that when you diagonalize a Hamiltonian, you essentially know what are the eigenenergies of the Hamiltonian. And when you know the eigenenergies of the Hamiltonian, you almost solve the problem, because many different observables are very easy to compute if you are in the diagonal basis, and excitations are directly let's say, not measurable, but computable if you are already in the diagonal basis. So for solving many problems, if your Hamiltonian is diagonal, you almost solve the problem. So most of the effort is actually in going from a basis that it's non-diagonal, and that is, let's say, the physical basis, to the diagonal basis that actually allows you to compute almost all the observables that you want. Yeah, great. Thanks a lot for the question. It was a very good question. All right, great. So in the following, let's focus on this interacting Hamiltonian. So a Hamiltonian that has maybe a single particle term, that it is not a problem for us anymore, but also has a many-body term. So a term that has 4 creation and annihilation operators. And this term is the one that it's very challenging for us to solve. And if we have a system with a few million atoms, certainly we cannot solve exactly, and we need to use some approximation. And as I mentioned before, let me emphasize that this interaction term, this term with 4 fermionic operators, is the term that is responsible for many different emergent phenomena in 2-dimensional materials. So if you think about any type of, let's say, magnetic 2-dimensional material, like let's say chromium iodine, chromium bromide, any other 2-dimensional bulk compound, the magnetism is driven by those electronic interactions. If you think about systems that have charge density waves, like, for example, to the quantum Hall states in 2-dimensional materials, and maybe also metallic dichalcogenides like niobium diselenide, charge density waves can also be potentially driven by electron-electron interactions. They can also be driven by electron phonon, of course. And then, of course, if you think about more sophisticated symmetry broken states, such as superconductors that break gauge symmetry, then those superconducting states, they are also driven by these terms that have 4 fermionic operators. So understanding how to describe those systems coming from or starting from 4 fermionic operators is, of course, very important for us. All right, great. So let's start maybe as an example with the simplest interacting Hamiltonian that we can think about. So we take a Hamiltonian that has some free particle dispersion that it's not critical for us. So that's the part that goes with Tij and a quadratic part. And then the term that is challenging for us is the one that is on the right. So the interaction term that in this form is called the Hubbard term. So it's an interaction that it's local in space, namely that only electrons that are on the same site I interact with electrons on site I. So in particular, up electrons interact with down electrons. So the basic idea is that this Hamiltonian already by itself is almost impossible to solve in any practical system. And of course, you are well aware that if you take this system in the square lattice, for example, this is already a problem that cannot be solved exactly. And it's a problem in which many decades of research effort have gone through. And of course, people have made a lot of progress, but it's still an open problem in the square lattice, just with first neighbor hopping. And of course, if you start considering much more complicated setups, like setups in which you have many hoppings at the same time, where you have spin orbit coupling effects, where you have, let's say, Moiré effects, or if you start combining different, let's say, materials with different dispersions, different use, then of course, in those instances, solving the problem is something that we will not be able to do in practice. So for those instances, we are going to use mean field theory. And the magic of mean field theory is that it is extremely good at predicting symmetry broken states, and in particular, many of the states that we described before. So if you take this Hamiltonian, just with the simplest electronic interaction, you can find 2 paradigmatic electronic states just by changing the sign of the interaction. If you take U smaller than 0, which is attractive interactions, you can directly find superconductivity in this model. If you take U bigger than 0, you can get magnetism. And just by playing with the electronic dispersion, you can get, let's say, conventional or unconventional superconductivity. You can get different forms of magnetism. You can get ferromagnets, you can get antiferromagnets, you can get frustrated magnets, and so forth. So this model already has a huge, very rich physical phenomena. Okay, so let's see how we can get both superconductivity and magnetism just in this very simple Hamiltonian. Let me emphasize that solving these mean field Hamiltonians is something that you will systematically do in the exercise sessions. So for superconductivity, as we mentioned before, we just need attractive interaction. So the whole trick of mean field theory is to think about what was our original problem and how to solve it. So our original problem was that we had terms that had 4 fermionic operators, and certainly we didn't like to have 4 fermionic operators. So if you are, let's say, a bit bold, you would say, well, a way of not having 4 fermionic operators is just by taking expectation value in 2 of them, right? And of course, you may think, well, this is not mathematically justified, right? If your Hamiltonian has 4 fermionic operators, you should keep the 4 fermionic operators all the time. Otherwise, you are changing your Hamiltonian in an uncontrollable way. And you are absolutely right. The bottom line is that if your electronic correlations are not very strong, then you can prove that the expectation values of terms with 4 fermionic operators are very close to the expectation values that you get if you start taking expectation values between 2 different fermionic operators. And again, let me emphasize that there's a very systematic way of proving when this works and when this doesn't work. But for us, for the practical point of view, what we are going to do systematically is every time that we have 4 field operators, we take expectation values in pairs. And in principle, we should take expectation values between all the pair combinations that we have there. And of course, if we switch the order of fermionic operators, we need to take care of the different signs that we get. For the computational sessions, you don't have to worry about that. Everything is done automatically. But let me just emphasize that for doing mean field theory, expectation values between 2 different fermionic operators, careful with the signs, all the combinations at the same time. All right, but for the case of superconductivity, the only combination that matters is the combination that has either 2 creation operators or 2 annihilation operators. So if you take u smaller than 0 and you solve this problem self-consistently, namely you start with an electronic structure, you compute the expectation values, these expectation values define a new Hamiltonian, you compute again your ground states, then you compute the expectation values, that these expectation values define a new Hamiltonian and so forth, and do this in a self-consistent way. What you actually get is that for u smaller than 0, that expectation value can be finite. And that expectation value is essentially the superconducting order, so the superconducting gap of a 2-dimensional material. You could, of course, have also done this with u bigger than 0, but if you compute this with u bigger than 0, you get that expectation value is 0. That is just something that comes from the self-consistent procedure. All right, so this was for superconductivity. Now let us move on to magnetism. So for magnetism, we start with the very same interacting Hamiltonian. So it was a Hubbard term that had density up, density down. But now for magnetism, what we do is to take expectation values between C dagger up, C up. And let me emphasize that we could also have taken C dagger up, C down. And if you do that, you also get magnetism, but it's a different type of magnetism. It's an in-plane magnetic order. But let's focus on this combination. So C dagger up, C up. So I mean, it is relatively easy to realize that C dagger up, C up is just the density of electrons up. So how many electrons with up spin do you have? And in the same way, C dagger down, C down is the density of electrons down, right? So now you can define your magnetic order as the density of electrons up minus the density of electrons down. And if throughout the self-consistent procedure, you get a difference that it's non-zero, so you get a finite magnetization, then you know that you have a magnetic system. And in particular, if you take an electronic structure, for example, at half filling with very large U, what you actually get is that you have a self-consistent solution that has a finite magnetic order.
What defines up here?
Sorry?
You put a specific direction to this up here. What was that?
Oh, that's a very good question. So it's actually arbitrary. So you can take any direction that you want, and you can see that even if you make a rotation in this Hamiltonian, you actually obtain this very same Hamiltonian. So the up direction is usually taken in the C direction, but you could have taken any other direction, and this kind of interaction is rotationally invariant. So it is, yeah, so I mean, there's another way of writing it. in which the rotational invariance is much more explicit, which is if you write, let's say, density up plus density down times density up plus density down. So of course, density up plus density down is rotational invariant because the total electronic density, and you would have total electronic density times total electronic density. And then if you expand that term, you get some term like this, and then a renormalization to the chemical potential. So the renormalization of the chemical potential, we are writing it down in the hopping term already. But in short, it doesn't matter which direction you take. Yeah, great.
So what completing term is necessary? We just get rid of it or
Oh, that's a very good question. So in principle, for the Hamiltonian that we have, we expect to have a Hamiltonian that is Hermitian, right? So a Hamiltonian in which, let's say, all the off-diagonal terms are the complex conjugate of each other, because those Hamiltonians can be diagonalized. And in principle, the description of quantum mechanics requires a Hermitian Hamiltonian. Of course, there can be systems that are described by Hamiltonians that are non-Hermitian, but for the purpose of this course, we are going to focus all the time on Hermitian Hamiltonians. Oh, that's the spin Pauli matrix. Yeah, so that's just one way of writing that difference, right? So the sigma z Pauli matrix is a matrix that has 1 minus 1 in the diagonal. So let's say that term is.
Seems like n is proportional to the difference. So you understand where it was n and the Pauli matrix.
Yeah.
No, it's not a proportional. So it's similar. Yeah, equal.
Yeah, so there it's unequal. So I put the.
It's unequal.
Yeah, it's unequal.
Okay. So isn't that described by the Pauli matrix?
So the idea is that if you kind of replace the m there in that formula, you essentially get the full expansion of the mean field. So this was just one way of rewriting it so that it is explicit that one gets an imbalance between up and down. But the basic idea is that, let's say, the second line and the line that is on the bottom right are just one way of writing the top line. Yeah, thanks. All right, good. So this is everything that we needed for understanding mean field. So we will essentially turn every Hamiltonian that has 4 fermionic operators into a Hamiltonian that has 2 fermionic operators by taking the, let's say, right contractions between the field operators. So now the last thing that we need to know is how to understand or how to compute electronic structures. And for this, let's just focus on a very, very simple example. So let's imagine that you have a one-dimensional system. You have a certain unit cell so that your system is periodic in space. And in each unit cell, you have a certain number of orbitals. So in this picture, you have 3 orbitals per unit cell. So the basic idea is that now in this second quantization formalism, you have field operators for every single orbital in every single cell. So alpha is the index that tells you in which orbital you are in the unit cell, and n tells you in which unit cell you are. So essentially, your full Hamiltonian is written in terms of these field operators. Now, the idea is that if you have translational symmetry, your Hamiltonian is written in a relatively simple way, namely that all the hopping matrices between the orbitals within the same unit cell are exactly the same, which is like saying that hopping between 1 and 2 in the first unit cell is exactly the same as hopping 1 and 2 in the second unit cell, in the third and the fourth, and so forth. And then the hoppings between orbitals in different cells is also the same as you move throughout the system. So hopping between the first cell and the second cell is the same as the second cell and the third cell, and so forth. So this is essentially one way of saying that your system has translational symmetry. And if you have translational symmetry, essentially your Hamiltonian commutes with the translation operator, and there's a basis in which you can simultaneously diagonalize the translation operator and the Hamiltonian. And this basis is the basis of block waves, or of plane waves. And the basic idea is that if you take that basis, which is just the Fourier transform of your field operators, you can write down the Hamiltonian in a very, very simple way. So in that basis, essentially, your Hamiltonian is written as epsilon phi alpha, psi dagger alpha, psi dagger, and psi dagger psi are just the eigenfunctions of the translation operator Oh, yes, this can be. Yeah, so these eigenfunctions here are the eigenfunctions of your translation operator that are at the same time eigenfunctions of your Hamiltonian, and these epsilon psi alpha are just the eigenvalues of your Hamiltonian. So this phase here, psi, is just the block phase that your wave functions have, and the basic idea is that to understand your Hamiltonian, you just need to know what is the relation between the energy and this phase, that is what we call the electronic dispersion. And in practice, if you have a certain Hamiltonian with a certain number of atoms in your unit cell, the only thing that you need to do is to diagonalize this matrix. The matrix of the entries that have the hoppings of the orbitals within the same unit cell and the hoppings between the orbitals in one unit cell and the next one. So in other words, if you have a unit cell that has 100 different orbitals, then what you have to do is to diagonalize a Hamiltonian that it's 100 times 100. Oh, see, HC, so that's a group. So HC is Hermitian conjugate. So it is essentially the term that you must add to your Hamiltonian so that the Hamiltonian is Hermitian by definition. All right, so in short, what we are going to focus on in the following is just on the relation between the eigenenergies of the block Hamiltonian that, as I mentioned, we can define as long as there's some translation operator in the Hamiltonian, and the momentum or the block phase. And of course, this is something that you already know from solid state physics. And the basic idea is that once we have this relation between the eigenvalues and the block phase, or the eigenvalues and our momentum operator, then we can define several quantities that are going to be useful for understanding many different properties of two-dimensional material. So the first quantity is the density of states, which essentially tells you how many states do you have that have a very specific energy that you target. So the density of states essentially tells you how many states do you have at energy omega. And the way one computes this is just by integrating the direct delta function in the whole Fermi, well, in the whole Bernoulli zone. Then the group velocity is essentially the derivative of the energy with respect to the momentum and tells you how fast, let's say, quote unquote, your electrons move. Then the effective mass is the second derivative, in the very same way as we define it in classical mechanics. And then the Fermi surface, for metals especially, is the collection of points in reciprocal space. So the collection of k points that have a very specific energy that you target. So it is kind of similar to the density of states, but resolved in momentum, let's say. And these concepts are, of course, something that we will be using over and over during the next few lectures. All right, great. So, and then the last thing that I wanted to tell you is about how some of the electronic dispersion that we will see. So, of course, from solid state physics, you know the parabolic dispersion, that it's something that appears in conventional semiconductors, and of course, it also appears in two-dimensional materials, such as different types of transition metal, dichalcogenides, particularly MOF2, tungsten diselenide, and so forth. Then another very important dispersion is the Dirac dispersion, so a dispersion in which the relation between energy and momentum is linear. And it's the dispersion that appears in graphene. And this type of dispersion is extremely important because it is the driving force of many topological and relativistic effects in two-dimensional materials. And then the last important dispersion is the flat band dispersion. So it's kind of the most boring dispersion, namely energy is no longer dependent on momentum. They are just a constant. But even though it looks like a very boring dispersion is actually the most interesting one because it gives rise to a huge variety of topological effects and also to strongly correlated effects, including magnetism, superconductivity, and so forth. All right, great. So I think that now it's a very good time for a short break. So I would suggest to have a 10-15-minute break. And during the break, of course, you can go outside and take some air. But if you want to think about something, I would ask you to think about this. So we've been talking about second quantization, right? So now my question to you is, what is the physical meaning of this term in a second quantized Hamiltonian? And the, let's say, first, clue for you is that I have not shown you this term so far. So think about what this actually means physically. So which kind of symmetry does it break, in which kind of material you may have it, and also for this term and also for this term. And we can briefly discuss about it after the break.